So good afternoon, everyone, and welcome to my presentation. So let me start the session. And first, let me introduce myself. I'm Hiroshi. I'm a product owner of one of our internal developer platform working for LY Corporation's private cloud division. LY Corporation is one of the largest internet companies in Japan, offering a wide variety of services such as communication apps, internet portals, news media, e-commerce, and so on. So we have been operating a large-scale Kubernetes-based platform for many years. And today's presentation is based on the experiences we've gained through running a lot of applications on the platform. And I contribute to CNCF Platform Engineering Committee Group. And in addition, I have written books on Kubernetes in Japanese. And my top priority in this presentation is to introduce my DIY keyboard to global audience. Yeah, this is my current desktop setup. Thank you. So anyway, today I'll talk about how to launch applications with greater stability and reliability on Kubernetes. I've organized my presentation into 3 key sections and conclusion. First, I will introduce what I mean with launch reliability and explain why it's important for production applications. And next, I'll share practical techniques for improving launch reliability. This includes tuning strategies for both container and application itself, and ensuring proper application initialization before accepting traffic. Then I'll discuss about a recent Kubernetes feature called in-place spot resize, which lets you change the amount of resources to container without restarting. And we'll explore how this can help with launch reliability. And finally, we'll wrap things up with a conclusion and key takeaways. All right, so let's get started with the introduction. First, let me explain how applications start on Kubernetes. When a pod resource is registered with the Kubernetes API server, the scheduler decides which node will run the pod. Each node has a kubelet that handles the preparations to launch the pod. The preparations include setting up networking and data volumes for the pod. And after that, the process of the application starts inside the container. Then the application performs various initializations. The application then reaches a state where it can execute its domain logic. For typical web applications, this means accepting traffic, processing requests, and returning responses. Once the application has been running for a while, it eventually reaches a stable state where it can work with maximum performance. And a common issue during startup is that applications start crashing and restarting repeatedly immediately after launch. You've likely experienced this during a rolling update with a deployment. Even the operation was working fine before, but suddenly it begins to fail. Of course, there are many possible causes for these failures. If it's simply due to incorrect environment variables, for example, that's an easy fix, but that's not our focus today. Instead, we'll address the more challenging scenarios. For example, crashes caused by slight performance degradation from minor code changes or library updates, or by unusually high amounts of traffic on newly starting pods. What makes these causes challenging is that these are unpredictable. The results come from slight performance degradations that accumulates over time or from sudden changes in external conditions, making them difficult to detect before they trigger the problems. In cloud-native environments, applications are frequently updated and scaled by design, so these situations can occur at any time without warning. By the way, this quote on the slide comes from rocket engineering. It seems the industry faces similar challenges. So let's explore how we can reduce these startup risks. When comparing applications during startup to those in a stable state, we see a number of important differences. For example, initialization processes run during startup, causing significant load and triggering frequent memory garbage collection. Similarly, applications with caching start with caches loading to higher latency. And there are a lot of other differences like I wrote on this slide. And these differences vary depending on the application architecture, language runtime, and framework it uses. But they all result in the almost same outcome. Applications immediately after startup cannot perform at their maximum capacity, right? So to prevent startup failures, we need to minimize the impact of these factors. Now let's explore specific practices, starting with tuning. First, let me explain why tuning is important for application startup. As mentioned in the previous section, applications have lower performance right after startup. But some factors listed on this slide can be addressed through proper tuning. For example, regarding garbage collection, increasing CPU allocation reduces the time spent on GC and reducing their negative impact on application performance. And another point worth mentioning is that applications on Kubernetes require tuning at different 2 layers. Container level tuning is done in Kubernetes manifest, which allocates CPU and memory to containers. And application level tuning means adjust parameters of language runtimes and frameworks, or optimizing application code for better performance. So let's start with container level tuning. In Kubernetes manifest, we can configure the amount of resources allocated to containers. For both CPU and memory, we can specify 2 settings, requests and limits. Request guarantees a minimum amount of resources that will always be available to the container. And limits define the maximum resources a container can use when using resources beyond the request. And for startup stability, it's good to set high values for both CPU and memory limits. This helps compensate for performance disadvantages. Additionally, if you set the request equal to the limit, It guarantees the resource availability for the application and further improves stability. However, even after the startup completes, these resources remain allocated for the container, so it reduces overall node resource utilization. Ideally, we would adjust the limits and the requests after the startup completes to release unnecessary resources. And we will explore methods for doing so in the third section. And another trade-off to container is quality of service, where Kubernetes assigns a rank to each pod based on its request and limit settings, which in turn determine the pod's eviction priority. Setting different values for requests and limits results in the burstable rank, making pod more likely to be evicted compared to pods with guaranteed rank. Also, be cautious when raising memory limits too high. If there's a large gap between actual usage and the limit setting, pods become more likely to be evicted compared to other pods even within the same burstable class. And this is a real example from one of our production applications. I actually added this slide just an hour ago. So sorry, the graph scaled and aligned. But still, you can see that by increasing the CPU limit, the latency degradation that used to occur during rolling update has disappeared. Now let's move on to application level tuning. Here we need to be aware of the effect of C groups. C groups is Linux kernel's resource control mechanism. It's how the host operating system manages container resources on Kubernetes nodes. And it enforces actual resource control based on the values specified in the resource limits. The tricky part is that C groups affect applications differently depending on language runtime, frameworks, and libraries. And this slide describes about such impacts to Java and Go runtimes, for example. Sorry, this table is a bit too detailed to read on the screen, so please download it later if you'd like to take a closer look. And we don't have enough time to dig into tuning methods for all languages and frameworks today. So I'll just introduce some practices for Java. Practically for memory management. And Java applications automatically set about 25% of the memory limits as the maximum amount of heap memory. This is usually too small, which means applications can't utilize the allocated memory even if you raise the limit. So I recommend increasing this percentage. If you add the configuration shown in this slide, the maximum heap memory will be set to 50% of the limit. By the way, some container build tools like packet build packs performs this kind of tuning during the container build process. And there's one more tip for Java. Java has a multiple GC algorithms. And if you don't specify one, the algorithm is selected automatically according to the limits value. So if you raise limits, memory limits without considering this, it may cause unintended behavior change. so be careful. Let's move on to the next category. In this section, we'll discuss ensuring applications are properly initialized before they start serving traffic. So far, I've used the term initialization several times, but what things actually happen during that process? This slide breaks down the application startup in detail. Please note that there may be some differences depending on the application, and we can see that initialization goes from the lower layers of the applications, such as the language runtime and standard libraries, and gradually moving up to higher layers. An important thing to note is that there's a moment when the application can start providing its functionality even before its state is completely stable. I created this diagram with web API applications in mind, and for example, in such applications, they might accept traffic even remaining some initialization steps. In such cases, API requests may fail or experience poor latency, which results in compromised startup stability. In other words, we should ensure that the application is sufficiently initialized before it starts serving traffic. Now let's switch to a more bird-eye perspective and look into how this application startup is managed at the Kubernetes pod level. The startup process we discussed in the previous slide corresponds to the main container shown with a red arrow in this diagram. You can see that various things happen around the startup of this container. The first step is to run init containers in the pod. They are executed sequentially if multiple init containers exist. After that, the main container is started and the post-start lifecycle hook is executed at the almost same time. When the post-start hook finishes, then the startup proof begins, and if it succeeds, readiness and liveness proofs start. After the readiness proof succeeds, the pod is marked as ready and start receiving requests. Therefore, we can support initialization using post-start lifecycle hook, startup proof, or readiness proof before external request comes in. Based on the mechanisms we've discussed, let's organize the best practices as shown on this slide. First, adjust your startup proof and readiness proof so that they succeed only after sufficient initialization. This can be achieved by simply delaying when the proof starts, or by configuring a health check endpoint not to return success until initialization completes. Next, ensure thorough initialization. For example, pre-fill database connection pools and thread pools. Many frameworks provide interfaces for defining such initialization logic, allowing you to ensure that health checks do not succeed until it has completed. Finally, if you need an even higher level of performance, you can also send actual warm-up traffic using a post-start hook or startup proof. Let me show you some actual examples. In this example, we are increasing the maximum size of the database connection pool to keep idle connections ready before the service goes live. This configuration example is for a Spring Boot application that uses a library called Hikari CP for connection pooling. Note that you'll need to find the appropriate way to apply the same settings for each framework. Here we are applying a similar approach with thread used for request handling. In this slide, we are not setting the maximum thread count equal to the maximum value because allocating too many threads means memory consumption remains high even when traffic is low. It's important to adjust this configuration with performance trade-offs in mind. And if you want to raise performance to near ideal levels during initialization, warm-up is another option. The example in this slide demonstrates how to send warm-up traffic to the application container. We are sending a request by executing curl commands using an exec type probe in the startup probe. With this approach, the curl command runs as a separate process inside the application container. And in this example, we are sending 10,000 requests because in Java, JIT compilation usually kicks in after the same piece of code has been executed about 10,000 times. And JIT compilation is the process where the runtime converts code into machine code. And it can significantly boost application performance. However, warm-up also introduces trade-offs, so it should only be applied when truly necessary. It adds complexity to the startup process and may increase startup time as well as a load on external systems, which the application depends. Now, let's shift our perspective and look at the recent Kubernetes feature that can help improve launch reliability. Specifically, we will take a look at a feature called in-place pod resize. In-place pod resize is a feature that allows changing resource requests and limits without restarting containers. As mentioned in the previous section, allocating more resources can help overcome low performance immediately after startup. We can potentially use this feature by allocating more resources until the application stabilizes, then reducing them to appropriate values once it becomes stable. My organization is considering using this approach in our platform. To be honest, we haven't put into production yet, but I'd like to share what we've learned from our evaluation so far. When using this feature for launch reliability, we can start by allocating a higher amount of resources and then decrease them after the application becomes stable. However, we need to be careful when reducing memory limits. If you lower the limit below the amount of memory actually being used, OOM kill may trigger and terminate the container. In the current implementation of this feature, Kubernetes performs checks to prevent this situation, but it doesn't fully guarantee safety. It's important to evaluate how well it works in a production-like environment before relying on it. And one simple way to avoid this risk is to reduce only CPU limits. And another approach may be to wait long enough between startup and production until memory usage has stabilized. We also need to be aware of how C groups affect language runtimes and frameworks. In particular, for this feature, it's important whether the runtime can dynamically respond when limits are reduced while the application is running. From this perspective, it seems we are still in early stages. For example, Java currently cannot dynamically reflect C groups changes. On the other hand, Go applications might be easier to adapt. This issue isn't limited to Java, of course. We'll need to wait for the broader ecosystem to catch up. And from an operations point of view, I think we'll need some level of automation for resizing when using this feature in production, since resize operations must be performed on each pod individually. Thanks to the community's efforts, in-place autoscaling in VPA seems to have been implemented. So I think this could be a good option to consider. And I've also been thinking about having a dedicated autoscaler for reducing resources only after startup. I think this could be valuable for two reasons. First, many teams want to use HPA for normal autoscaling and would prefer to use resizing only after startup. Second, resource consumption patterns differ significantly between startup and normal load fluctuations. So we need separate conditions for triggering scaling. And I'd appreciate any feedback on this idea, and if it seems useful, I'd like to try implementing a prototype. Finally, let me briefly summarize and conclude this session. First, I explained why improving launch reliability is important. Startup problems are difficult to predict and can happen at any time. Next, I introduced practices to enhance launch reliability. I explained the need to understand the relationship between application behavior and Kubernetes controls to implement effective measures. Finally, I discussed how in-place pod resize could be applied to this topic. This feature will need careful consideration before production use. I look forward to contributing to its development with the community. Yeah, thank you for listening. My content is, that's all my contents. If you have any questions, I'd happy to answer them now. Any questions? Thank you so much. Yeah. Come to the mic, yeah.
As far as using some of these new features within Kubernetes for auto-scaling and what has recently been released in 1.33, what's been your experience with Java applications and getting them to be able to reliably use some of these auto-scaling things when Java natively doesn't do very well in that kind of dynamic environment?
Sorry, we have not tried the Java applications to impress pod resize. We started to trying with Go applications. So I have no idea of the actual what happening in that situation. I'm so sorry. So does it make sense?
Yeah, thank you.
Thank you so much. Yeah, thank you for listening and enjoy KubeCon.